today we'll continue our discussion on optical transmitters and specifically discuss light emitting diodes. So in the last class we discussed some basic semiconductor physics on which sort of these optical sources are made using this forward bias p-n junction and specifically this double heterojunction structure to increase sort of the radiative recombination of the carrier so that the device is more efficient and more light is emitted, right? So if you just take a structure like that, just like this double heterojunction, so you have an N layer, then an active layer, then a P layer, and that's it, you don't do anything else to the device, then such a device will act as a light emitting diode. Okay. So in the forward bias region, if we pass some current through it, there's some light emitted out of the device, right? And this light, if you don't do anything else extra to this device, then this sort of the emission is, we'll see over sort of broad band, right? And the light is not totally coherent, so so that's the LED regime of operation. We'll see later how once we do some extra special things to this device, like for example, polish the facets and make a cavity, then we can get optical feedback, and then we can go into the lasing region. Okay, but let's first discuss LEDs, which are used sort of nowadays not so much, but as I said earlier, like for some short links. Now people are trying to go to optical fibers even for short distances, like within metro areas or even within data servers or within buildings. So for those kind of short links, we can still use LEDs. Okay. So basically, we had this kind of structure, right? So in the active region where the band gap was slightly lower, sort of these carriers are accumulating, right? And then basically, if they radiatively recombine, then they can give out light. Right? So this is not the only process by which sort of we can lose carriers from the active region, right? This is what we want, that the electrons should combine with the holes to release a photon, which is called radiative recombination. But there are other processes by which we can lose carriers. For example, you could have some defects or trap states, right? So you can imagine like this material is not perfect. There are some bonds which are broken in certain places. So those will add some extra energy levels. Okay? And the electrons or holes can actually go there and like sit in these traps. Okay. Also, like every device will have some surface, right? And of course, the surface, like on the bottom side, you have on the top surface, for example, bottom side you have the material, but abruptly the material stops. On the other side, you have like air or something else, right? So of course, there are dangling bonds on the surface also. So these surface traps also exist, right? And then like you could have some phonon-assisted processes where sort of the charge carriers give away energy to the lattice vibration in the medium. Okay. So all these non-radiative processes can also cause the carrier concentration in the active region to decrease. Okay. But we want that to be very small, right, compared to like the radiative rate, because our purpose is to get light out, right? So there is this parameter defined, which is known as the internal quantum efficiency. Okay, it's denoted by this symbol eta. So it's the radiative rate. Okay, so the rate at which the carriers recombine to emit light, right, divided by the total recombination rate, which we can write as a non-radiative rate and a radiative rate. Right, so it's basically like the fraction of charge carriers which are combining through radiative means. So of course you want this number as high as possible, right? So the maximum this number can be is 1. So you want this as close to 1 as possible. for a good efficient device. Right, so this R basically is the rate at which the carriers are recombined. So basically, if N is the carrier concentration in the active region, the rate at which this carrier concentration is decreasing due to recombination, that's this R. Okay, so this can be modeled as sort of by the simple expression where we say basically the charge carriers stay for some finite amount of time here, called the charge carrier lifetime, tau sub c, before they recombine. Okay. So if we write total rate here as a sum of the non-radiative and the radiative rate, we can define a non-radiative time constant plus a radiative time constant. Okay. So you can see that the total lifetime of the carriers is this inverse sum of the radiative and non-radiative. Right. So the total carrier lifetime here in the active region is a harmonic mean of the non-radiative and radiative light. Right. So you can see that basically, so tau c will be less than both tau nr and tau r. Okay. So this is the non-radiative rate and this is the radiative rate. And by this definition, if we use this expression, then in terms of the time constant, you can see that this internal quantum efficiency is related to the non-radiative and radiative lifetimes like that. Right? So basically for a high quantum efficiency, we want the non-radiative lifetime to be much larger than the radiative lifetime. Right? So the non-radiative, so again, what is the lifetime? That is the sort of the mean amount of time that the carriers stay before they recombine, right? So if the radiative lifetime is much smaller, then the probability is very high that the charge carrier will first recombine radiatively rather than non-radiative, right? Because the lifetime for non-radiative recombination is much larger, right? So you can see basically in terms of the lifetime, we want the non-radiative lifetime to be much larger, or in terms of the rate, we want the radiative rate to be much larger. Okay, so if you look at some typical materials, so for example, if you look at indirect band gap materials, we know that the radiative recombination is not very efficient because you need some phonon assisted mechanism to conserve momentum when the charge carriers sort of come down from the conduction band to the valence band, right? So, so if you look at, for example, silicon, germanium, or typical semiconductor materials from group 4 which have indirect band gap, this quantum efficiency is extremely small. Okay, like 10 to the minus 5 or something. So most of the carriers recombine non-radiatively. That's why you don't get any light out of the device. Okay. Whereas if you go to direct band gap, so these 3-5 materials that we talked about, right? You can really increase this a lot. So this can be up to 50% for this gas or in gas P materials that we talked about, right? And if you again go for this double heterojunction, that can even improve the quantum efficiency a little bit more. So typical devices nowadays like have between, let's say, 60 to 80% quantum efficiency. Okay, so you can see that these devices are quite efficient, right? So these non-radiative recombinations also affect the performance in terms of, for example, all that. So these coupling to the phonons is basically dissipated as heat in the medium, right? And we'll see basically, so if the temperature of the device increases, then the performance also drops. Okay, so for various reasons, you don't want this non-radiative process to be very strong. Okay, so let's look at the power current characteristics, or also known as like Li curve. Right, so how much light do I get out of the device if I pass a certain current through it, right? So again, let's say right, so this is my device, so P, N, and then a thin active region in the middle, right? And recall that the light is being emitted from the active region, right? And so we pass a current like this, we forward bias PN junction, and we inject a current I, right? So there is some optical power coming out here, P out of the device. So we want to know basically for a given amount of current I, how much optical power we are getting out, right? What we are interested in finding. So due to this current, right? So current is basically the flow of charge carriers, right? So we're injecting electrons and holes into the medium. So there is a rate at which we are injecting carriers from outside into the device. So this injection rate is basically just the current divided by the electronic charge, because the current is the total charge flowing per unit time. So if we divide by the electronic charge, we get the number of charge carriers moving per unit time, right? So that's the number of charge carriers which are coming into the device, right? Or you're going to be leaving the device. Okay, so basically in steady state, so of course, as soon as you switch on, like if you have a switch here and you close this circuit, there will be some transients in the beginning, but eventually it will reach a steady state, right? Such that the number of carriers in the active region in the device here is some constant. Okay, it's not varying with time. So the rate at which the carriers are sort of coming in and leaving and recombining in the middle are the same, right? So basically we reach some steady state where, so now if you look at the rate of change of the carrier concentration, so the carriers are being injected due to this current I, right? So that's an increase, right? And then from here we can see that due to the recombination, they're going down, right? So here dN by dt is basically minus n by tau c, right? So this is the injection rate, and this is the recombination rate. Okay. So in steady state, basically this rate of change becomes 0. Okay. And now if you look at the rate of charge carriers which are combining radiatively, right? That's basically right, this n over tau r, right? So I can write that as, so Right. So this is basically the number of charge carriers recombining per second to emit photons. Right. That's basically the internal quantum efficiency. Okay. So if we write the expression for tau c in terms of tau nr and tau r, right? And then we read the radiative recombination rate here is n over tau r. Then basically we'll see that this rate is just, we can write it as the internal quantum efficiency times I over q, right? Which also makes sense because, so recall this I over q is the number of charge carriers which are coming into the device, right? And in steady state, basically, this rate is equal to the total recombination rate, and out of them, how many are recombining radiatively is basically the internal quantum efficiency, right? Which is the fraction of charge carriers which combine radiatively. Right. So basically, this is also equal to the number of photons being generated in the device per second, right? Right. So each radiative recombination is giving me a photon. So this is also the number of photons generated per second internally within the device. Right. So if you multiply by the photon energy h nu, then we get basically the power. So the optical power which is generated internally is this just number multiplied by, so P internal right. So this is n, right. So internal quantum efficiency times current divided by the electronic charge times the photon energy. And recall this photon energy is basically just the band gap. I mean, so we'll see that not all the photons have exactly the same energy as the band gap, but roughly we can say, okay, it's band gap. Okay, so roughly we can say basically this is also just equal to, so we replace h nu by the band gap. Okay, so now this is the sort of number of photons being generated here inside internally in the device. Okay, but of course, what we are finally interested in is what is the power coming out of the device, right? Which we can, for example, couple into an optical fiber or whatever. Right, so not all the light which is generated inside the device escapes out. So there is also what is known as an external quantum efficiency, which is basically the fraction of light escaping out of the device. So by the way, these lifetimes typically for these 3-5 semiconductors are typically in the few nanosecond range. So let's say between 1 and 5 nanoseconds somewhere. Okay, so if you look at this device here from the side, for example, you have a P region, active region, N region, and the light is generated in the active region, right? So when we are operating in the LED regime, right, basically just the carriers are recombining and there is no preferred direction to emit the photon, right? So basically it can emit in any random direction, but of course we want to see like how much, let's say we are collecting from the top, how much is coming out. Okay, so you can see that as this angle of emission increases, right? At some particular point, so this is the material refractive index, and outside, let's say it's air, right? So here n is equal to 1. Here the refractive index typically of these materials are like between 3.3 to 3.5. Okay, so quite a high refractive index. So again, the light is going from a denser medium to a rarer medium. So that means that beyond a critical angle, the light will actually get internally reflected. Okay. So basically, there is a particular angle right up to which the light will come out. So there is a cone of some angle here, theta c, right? And of course, that theta c is just sine inverse 1 over n from the Snell's law, right? So n is the material refractive index again. Typically 3.3 to 3.5, somewhere in that range. Right. So this angle you can see is 1 over sine inverse 1 over 3 point. So this angle is quite small. Typically like 10-20 degrees, not more than that. Okay. So rest of the light sort of remains trapped within the device and then finally is like somewhere internally absorbed or scattered away. Okay. So a very small fraction within this cone is coming out. Okay. So to estimate basically, right. So what is the fraction of light for, compared to the total amount of light that is being generated internally, right? So that fraction is basically this external quantum efficiency, right? So we can calculate that like this. So the light is emitted over the whole 4 pi solid angle, right? So you can assume like each point here is like a point source, so it's emitting in all direction spherically symmetric, right? So it's radiating over the whole 4 pi solid angle. But the angle that we are able to collect is between, again, this 0 and theta c, right? So there is some transmission coefficient, right? So even for rays which are less than the critical angle, you know that there is some transmission coefficient, right? So it's not 100% transmission, there is some reflection and then some transmission. Beyond the critical angle, 100% is reflected. So there is some transmission coefficient here, right? So this is basically the Fresnel transmittivity at incidence angle theta. Right, multiplied by the right. So if you work in spherical coordinates, so there is this angle theta, right, which goes from 0 to pi, and then there is this phi angle, right, which is going around, that is from 0 to 2 pi. So this is symmetric in the phi direction. So we just integrate over phi to get 2 pi. And then with theta, we have this transmission coefficient depending on theta, right? So you know that the differential element for the solid angle is sort of sine theta d phi, right? So d phi we integrate with 2 pi, and then we have the portion for theta remaining, right? And you know, so we know the expression for this, right? It has something like n sine theta minus. So n1 sine theta minus n2 square. So n1 sine theta I minus n2 sine theta t divided by n2 sine theta I plus n1 sine theta t, some expression like that, right? So of course we can take the whole expression as a function of theta, and then but that integral will become complicated, right? So you'll have functions of sine of the angle in the numerator denominator, and okay, so that integral is not easy to solve. You can numerically do it, right? But to estimate, we can actually make a simplification just because this n is very large, right? 3.5. So this angle theta c is very small, as I said. So typically like 10 degrees or something. So basically, close to normal rays are coming out, right? And all the rest of the rays are not coming out. So the angle of incidence is quite close to normal. Okay. So basically, we say that so for theta c very small, so much smaller than 1. So in this case, it's or in other words, basically theta c is close to 0. We just approximate this transmission coefficient for all theta as the transmission coefficient for normal impedance. Okay, noting that the deviation will only be a few percent for angles up to 10 degrees or so. Okay, so then this is a constant now, right? So this is just a normal incidence transmission. So that you know is just sort of n minus 1 by n plus 1, or that's the reflection coefficient. The transmission coefficient is just (4n by n plus 1 square). Okay. Okay, so basically we get rid of this theta dependence here. So of course this sort of slightly overestimates the power coming out, but the deviation is not too much. Few percent. Okay, maybe I should erase this. So the internal power generated here, we had an expression here. I'll leave that. Okay, so now the integral for this external quantum efficiency is very simple. Okay, so you have an integral of sine theta here, so you get cos theta, right? And the limit here is sine inverse of 1 by n. So you can convert this to, so if sine is 1 by n, you know cos is square root of 1 minus 1 over n squared, right? So you'll get something like that here. And then we make another further simplification that again so if n is greater than 3, which is the case for these materials here, n square is like close to 10, so that's much bigger than 1. Okay, so here for example, so cosine theta you'll get something like 1 minus 1 over n square, right? So you can neglect this 1 over n square with respect to 1. Okay, so this expression just ends up being okay. So just do this integral at home, find the total expression, and then use this approximation to get this. Okay, so I'm not going through all the steps. Okay, so you can see basically this external quantum efficiency is sort of going as 1 over the cube of the refractive index, right? So higher the refractive index of the material here, the worse the light collection up, right? And for these 3-5 devices, this n is actually pretty large. So if you put, for example, n equal to 3.5, this number comes out to be only like 1.4%, 0.0014, right? Which is very small. So you can see like roughly 1% of the light is coming out of the total light is being generated. So that's really poor, right? So in some cases, certain things are done to improve the light collection. Sometimes like some lens kind of structure is made on top here, like you put like a glass dome of something so first of all you decrease the index contrast, right? So that the critical angle becomes larger, and then this sort of lens kind of design also sort of collimate light which is coming out into a particular direction. Okay, so but of course then it becomes more complicated, right? So then you have to now integrate optical elements on top of this electronic chip that you've made, right? But if you want to increase the external quantum efficiency, there are ways of doing it like that. Okay, so you can see, yeah, so the total power coming out of the device, so the P external is basically the external quantum efficiency times the internal power generated. So this is equal to okay. So basically the optical power coming out of the device scales linearly with the current, right? So this Li curve that we were talking about, so it's like a straight line. This is the optical power coming out versus input current, right? And the slope of this line depends on the band gap, right? Which depends on the materials they use, and then this internal and external quantum efficiency, right? So higher these numbers, higher the slope, and more efficient the device. Right, so you can see that the total efficiency, which is the product of these two, is quite small, right? So internal quantum efficiency is set between, let's say, 60 to 80%, external quantum efficiency 1%. So the overall efficiency is less than 1%. Okay, and not only that, so again, like even if so if you don't try to do something fancy like having a ball lens on top or something like that, the light which is coming out is not all coming out parallel, right? So there is some small spread of angles. So this acts as what is known as a Lambertian source, right? It's unlike a laser which gives out directed light. The LED actually gives out light at a spread of angles. Okay, so if I look at the intensity at angle theta from the normal, okay, so that goes something like cosine theta. Okay, and remember now, let's say for communication, we want to couple this into an optical fiber, right? So for a laser, when all the rays coming out are parallel, it's easy to like use a lens and then focus it on into the fiber. But for this diverging kind of source, the coupling efficiency into the optical fiber also goes down. Okay, so typically, like the coupling efficiency that you get goes as the square of the numerical aperture of the fiber. Okay, for such a source. So typically, so numerical aperture, recall, was something like, so square of the numerical aperture would be the n1 square minus n2 square. Right? N1 is the core index, n2 is the cladding index. So if you take a typical single mode fiber, the Na is quite small. Okay, so let's say between 0.1 to 0.3 or something. It's closer to 0.1 typically. Right, so the coupling efficiency is the square of this, right? So you can see that's only like 1% or so. So definitely less than 10%. right? So if you want to finally, if you're interested in how much power is coupled into the fiber, that's an additional coupling coefficient here, which is again like 1 to 2%. Okay, so that again decreases the power by more than an order of magnitude. So for these reasons, basically, with LEDs, you're not getting much power into the fiber for communications. Okay, so typical values here are, so the internal power, typically you can get, let's say, in the 10 milliwatt range, tens of milliwatts. Okay, the external power reduces to less than 100 microwatt, because again, mostly this external efficiency is very small, right, 1%. And then if you are looking for the power coupled into fiber, then that goes down even further to, let's say, 10 microwatt or smaller. Okay, so with LEDs, that's the kind of powers you're looking at in your fiber for communication. Okay, so you can see that that's really tiny, right? So with lasers, we typically work with tens of milliwatts. With LEDs, we are talking about microwatts, so 3 orders of magnitude lower. Right, and not only that, so you have lower power and also it's spread over broader bandwidth, right? So for example, you get more dispersion, more dispersive broadening as you go into the fiber. Okay. So of course, I mean, you know this already, that the performance with LEDs is much worse compared to lasers, but it can still be good enough for certain very short links. And they're also being used for some other communication applications, like for example, free space optical communications, where instead of fibers, we want to send actually free space optical signals. And so one application for that is actually, for example, indoors, we want to replace our traditional Wi-Fi signals, which work in the microwave region, right, with what is known as Li-Fi, right? So the LEDs that we use for illumination, if we can also modulate signals onto that, and that light coming from the LED is being modulated, and then your receiver is has a photo detector which detects that light, and actually, so you're connecting to the network like that, right? So LEDs are still being explored for these kinds of applications. Okay, so finally, there's a metric which is known as the total quantum efficiency, or the power conversion efficiency, or sometimes the wall plug efficiency. Right, so basically, I'm finally interested in how much optical power I'm getting out, right, divided by the electrical power I'm putting in to the device. Right, so I can write this as so V0 is the, I've removed that figure, but yeah, so let's say if V0 is the forward bias voltage, right, so V0 times I is the electrical power input. Okay, typically this forward bias voltage is of the order of the band gap. So basically, Eg is Q times V0 roughly. Right, so Eg is around like 1 electron volt. and the voltage is applied here is also around 1 volt, right? So again, recall this picture of like you had this band bending and then you wanted to apply some voltage to make this sort of flat so that current can easily flow. So the amount, you can see that the amount that we need to push this up is roughly equal to the band gap. Okay, so that's the sort of the forward bias voltage which is used, is roughly of the order of band gap divided by electronic charge. So if you use this here, then you can see that this cancels out, then QV also cancels out with EG, and this is just the product of the external and internal quantum efficiency, which of course makes sense, right? The total efficiency is the product of the external. Okay, so this is typically less than 1% for LED. The total efficiency is less than 1%. We'll see that when we discuss lasers, this particular quantity, the total efficiency will be much higher, right? Close to like maybe 30%, 40%. Okay. So a laser is much more efficient in converting the input electrical energy to optical. Okay, so basically this efficiency is also telling me, like, again, what is this slope, right, of the optical power versus input current. So there is another quantity which is defined that you might come across in literature, for example. Okay, so that is known as the responsivity of the LED. That is the optical power coming out divided by the input current. Okay, so this particular term also comes when we study photodetectors. Photodetectors are often defined in terms of their responsivity. So there we define basically the current generated per unit optical power incident on the device, right? So here is sort of the opposite, the optical power generated per unit input current. So you can see the units here are watt per ampere. So again, using this expression for the optical power, this just comes out to be the external efficiency times the internal efficiency times that. So it's the total efficiency times the band gap, right, or the total efficiency times the forward voltage. Right. So again, if the efficiency is higher, this responsivity is higher. It's just a different way of saying how efficient the device is. So again, if you could take a typical C5 LED, this number is about 0.01 watt per amp. Okay, so let's say if you send in a typical current of, so if you send 1 ampere current, you get 10 milliwatts. And 1 amp is sort of the max limit of the current that you typically send into these devices. So that's sort of the maximum. I mean, typical operating currents are sort of in the 100 milliampere range. So yeah, so basically what this is telling us is what is the slope of the optical power versus current, right? So So another thing to note is that this slope actually depends on the temperature. So first of all, this linear characteristic only sort of works till about a certain current, which is typically again like roughly 100 milliampere. Okay, after which this curve sort of starts saturating. Okay. And basically what is happening is that beyond a certain current, now you're sending so many charge carriers into the active region that now you increase the non-radiative rates. Okay. So for example, you have like collisions between charge carriers, collisions between the charge carriers and the atomic defects, etc., which increases the non-radiative rate. Okay. And also increases, for example, the heat dissipation in the device. So the fraction, the radiative rate or the internal quantum efficiency starts going down. Okay. So this curve starts saturating beyond a particular current. And not only that, this depends on temperature. Okay. So if you operate at a higher temperature, then the slope is actually slightly lower and also starts to saturate faster. So okay. So that's another reason why you want as high internal quantum efficiency and radiative recombination as possible, because any non-radiative recombination also actually increases your heat dissipation and internal temperature of the device. Okay, and basically again, what is happening with increasing temperature is like you are increasing the defects, traps within the material, which increases your also these collisions between charge carriers, which increases the non-radiative recombination.
Sir,
Yeah.
uh, previously you said that external power of LED is in microwatt, right?
Yeah, yeah. So here, I mean, so this is like a very good LED. So maybe, yeah, probably maybe it has some more uh, better collection outside. Uh, Also, so there is a difference between like the top surface emitting and edge emitting, right? So we said that. Uh, so what we sort of calculated was sort of like the top emission, right? Surface emitting. You can also have edge emitting, right? Where basically now you have a larger sort of region contributing to the emission, right? So the external efficiency for the edge emitting can be slightly larger. And then also you can boost it again with these external collection optics if you want to integrate. But yeah, the absolute numbers depend on the particular LED. Right, again, so as I said, typically operating currents are sort of in this range. Right, beyond this, you can see that it's sort of saturating and the device actually, but if you operate beyond this region, then you're actually damaging the device because you're creating more and more defects. And over time, that device will actually fail. Right, so typically you want to operate, let's say, up to 100 milliamp current, and there you can see that, let's say, at room temperature, right? So the powers are, let's say, around millivolts. Right? So that would be a very good LED. Typically, you would have the 10 to 100 microwatt in that range for a standard cheap LED. Okay. So right, but this behavior is consistent. Like the absolute numbers will change from LED to LED, but this behavior of increasing with increasing temperature, the slope going down and the saturation happening Earlier will be same for all the LEDs. Okay, so that's sort of the luminosity curve or the Li curve. Then the other property that we are interested in is in the spectrum, right? So what wavelengths are coming out? So of course, sort of the center wavelengths that we design for is basically given by the band gap, right? So that's sort of like the main wavelengths coming out, but of course there's a spread. Right, and this spread, recall, is coming from so if you again look at the conduction band and the valence band, so the carriers occupied some range of energy levels here, right? It is not that all of them were here and then all the holes were here and the recombination happened exactly from the bottom of the conduction to the top of the valence band. In that case, exactly it will be Eg. But there is a spread of energy levels over which the electrons are distributed here, and there is also a spread of energy levels for which the holes are distributed here. And we saw that this was roughly like the thermal energy KBT. Right? So you can see that this recombination can happen over a range right, of the thermal energy around the band gap. Okay, and so if you look at, for example, the spectrum, let's say was the wavelength of frequency. So we can approximate the spectrum here like this. So there's a factor which is goes at the square root maybe I should say mu here instead of omega. Okay, so there is a factor which goes in the square root of the energy. So recall that this distribution was coming from a product of two quantities, right? One was like the density of states, which went as the square root of the energy here, right? Here, right? So that is contributing to the square root of the right. So the photon energy minus the band gap. And then there's an exponential factor here, which is coming from the Boltzmann distribution. Right, so this is coming from basically this occupation probability. Right, so we had this Fermi-Dirac distribution, whose basically tail is sort of coming in here, right? And this tail can be approximated by an exponential function. Right, so again, you might have heard about Boltzmann statistics or Maxwell-Boltzmann statistics, which is just an exponential function in the energy divided by the thermal energy, which is a sort of high energy limit of this Fermi-Dirac distribution. Okay, so basically the spectrum can be approximated from the product of these two functions coming from the density of states and the occupation property of the carriers. So right, so you can see actually sort of like the minimum, like you have wavelengths bigger than Eg. And this maximum occurs here. If you maximize this function as with respect to nu, this maximum occurs at Eg plus kBt by 2. So this is frequency scale, and we have to divide it by h. Okay, so you can see basically the maximum power is being emitted at a frequency which is slightly higher than the band gap, right? So because you can see that the carrier distribution here peaks at somewhere slightly higher than the band gap. So the wavelength or the power on the frequency at which the maximum energy is emitted is slightly larger than the band gap, plus by half the thermal range. Okay, you can also calculate like a spectral width here. If you calculate the full width at half maximum, the spectral width also depends, of course, now again on kBt. It's about 1.8 kBt by h. Okay, that's the spectral width here. Okay, so you can see for an LED, how broad the spectrum is just determined by the temperature at which you are operating, because it gives you the spread of energies over which these charge carriers are distributed, right? So it gives you a spread in the frequencies of the emitted photons. So, for example, if you put again room temperature here 300 Kelvin, this comes out to be about 11 terahertz, right? So that's very broad. For lasers, we typically talk about gigahertz, megahertz, or even kilohertz line widths. Here for LEDs, we are talking about many terahertz. Okay. So it's a very broadband incoherent source. Right. So if you plot it in wavelength, right? Then of course you'll see something similar with the spread in the wavelength given by this quantity, right? So you can see that in frequency it does not depend on the band gap or the emission center wavelength, for example. It just depends on temperature in frequency scale. But in wavelength scale, it will depend on which wavelength you're operating at or what is the band gap, right? So, for example, if I take gallium arsenide based LED where the emission wavelength is roughly 850 nanometer, okay, then this delta lambda comes out to be about 35 nanometer. Okay, so you can see it's really quite broad. Like it's a few percent of the center frequency. If you go to the other material system in gas P, then for example, if you go to 1.3 micron, this delta lambda comes out to be like 120 nanometer. Okay, again, like if you go, so this is sort of assuming like a surface emission, right? If you go for an edge emission like this, so then basically a lot of the light is sort of internally reflected and then reabsorbed within the device. Okay, and this spectrum can become slightly narrower for edge emitting. So for surface emitting, if that's the number, for edge emitting, like this delta lambda can be lowered to like maybe 75 nanometer. Okay. And there are again some tricks that people can play to sort of make this narrower. So try to introduce some internal absorption within the device itself to sort of cut out these other wavelengths. Okay. And sort of preferentially emit here. So they are called superluminescent LEDs or SLEDs. S stands for superluminescent. Okay, so there they can reduce the line width to like typically tens of nanometers. So this is like less than 50 nanometers for infrared wavelengths in like from 1.3 to 1.6 micron in that range. Okay, so you can think of this as being somewhere in between, sort of like a LED and a laser diode. This SLED. Okay, so yeah, that's sort of the. So best SLEDs maybe have like 20 nanometer, 20 to 30 nanometer bandwidth, something like that. The laser diodes have bandwidth between like 1 and 10 nanometer. And then once you stabilize the laser cavity, so we'll study more about how we do that for the semiconductor lasers, then you can get into like really narrow bandwidths. Anyway, so that's as far as the spectrum is concerned. And then the final property that we are interested in, for especially for communication, is so we want to put electrical data, right, onto this light emitted, right, and then send the optical signal forward. So one direct way to, of course, do that is we are sending this current, right, and we saw that the power is proportional to the current. So if we can just directly modulate the current going into the device here, right, according to our bit stream or electrical data, then the optical power coming out should also get modulated, right? So of course we want to see like how fast we can do this, right? So we'll see, of course, there is some limit to how fast we can do this. So that limits the data rate for direct modulation, direct current modulation. Right, but in the early days, this is how before like electro-optic modulators were invented. This is how like electrical data was transferred to the optical domain, and you can still do this for certain. So this Li-Fi application that I was talking about inside the room using the LEDs that we use for illumination also to transfer data. There we are still exploring this direct current modulation technology because again for Wi-Fi, you know that the data rates currently that we get with Wi-Fi are maybe few megabit per second, right? Is really good. So with current modulation, as we can see, we can go to hundreds of megabit per second, easy. Okay, so for this kind of application, that is still a big improvement. But of course, if you want to do optical fiber communication, carrying lots of data over long distances, of course, that's not enough. Okay, so again, we have this device here. I'm sending current. Right. So let's say the device could have some cross section here. So length L, width W, and then the thickness of the active region is some D, right? Which we saw that typically it's like maybe 100 to 200 nanometers in that range. Okay, so again, if you look at the carrier concentration in the active region here, right? We saw that you can write the rate of change of the carrier concentration in the active region as a sum of two parts. This is the due to the carriers injected due to the current into the device, and then this is due to the recombination happening in the active region. Of course, if you have a DC current, steady current here, then eventually this becomes zero, right? And we have a steady concentration here of charge carriers, which are recombining at some rate and giving me a constant power, right? But now we are interested in modulating this, right? So sending some time varying current. So if this current is now time varying, of course you can see that this will also be time varying, right? Which will give me a time varying optical output. Can you talk about the limitations of lifetime on the possible data rates? Yeah, so we'll see, right? So again, we want to find out how fast we can modulate this such that the optical power coming out, right, also follows that same rate, right? And we'll see that that will be limited by the lifetime CFI. Okay, so we'll see how that limitation arises. Okay, so this V here is the volume. Okay, so this N is the carrier concentration, right? So let's say per centimeter cube or something. So this is the volume of the active region. So this is in the active region. So this is volume of active region, which is, you can see here, the length of the device times the width times the thickness of the active region. So typically length and width are maybe tens of microns, and D is like 100, 200 nanometers. Okay, sometimes you'll see this in terms of the current density. So I over V. So I can write as the current density J into the cross-sectional area, so W times L, and here volume is W times L times D. Okay, so this J is the current density in amp per centimeter square. Okay, so this is more like a material quantity, right? Because we take out the device dimensions out of the equation, right? So this is J over D. So sometimes this is also written as J divided by QD. Okay, but J is the current density. Anyway, so if this current is a DC current, right? So then, so for I equal to some IDC, which is constant, right? So then this eventually becomes zero, and you can see that like there's a DC concentration of charge carriers, which is just given by that. Right, so I just put this equal to 0 and find N. But now, let's say I have a time varying current. Right, so the simplest possible thing I can have is like a sinusoidal current at some particular frequency. right? And any other signal I can always write as a from Fourier transform as like a superposition of different frequencies, right? So to obtain the frequency response of the system, I can analyze it in terms of, let's say I send a current which has a DC component, which is known as the bias current. Okay, and then I have a time varying sinusoidally varying current at frequency omega m, right, which is like my modulating frequency. Okay, so now you can see for this I bias, which is a constant term, I'll get a corresponding constant carrier concentration NB. Time varying term will be a time varying carrier concentration. Okay, so this is just a linear differential equation, right? So if I drive it at some particular frequency, I can write the solution as also at the same frequency. Okay, it's like driving a pendulum, applying a force at a particular frequency. The pendulum will also respond at that same frequency. Okay, so it's like that. Right, so we know, so now we already know, so NB we can write from here like this. Right, so what we are doing here is, so again, recall that the optical power versus current curve was linear. So we are operating at a bias point here, IB. Okay, and then applying a sinusoidal modulation of amplitude IM. Right, and so that will give me an optical power out here, right? So some DC power here, PB, and then some AC part which has amplitude PM. Okay, so if we plug this solution here into this equation, right, and then just compare the coefficients of this e to the I omega mt part on both sides, because this solution has to be valid for all time, right? So basically, the only way that is possible is that the coefficient of this e to the I term on both sides are equal. So you can just do that straightforward. So we can get Nm in terms of Im. Okay, so Nm not only depends on Im, like just like Nb depends on Ib. But it also is frequency dependent, right? Because of this term here, dn by dt, right? So that will give me I omega out front, right? So here I'll get an I omega n, right? Which is what is coming here. So when we add it with this tau c. Okay, so you can see that now this amplitude of the time varying charge concentration not only depends on the current but also on the frequency. And more specifically, the frequency is coming in the denominator, right? So as I increase the frequency, this Nm will go down for the same Im, right? Which means that this Pm will go down, right? Because what is, again, we calculated the power emitted is basically the number of charge carriers combining radiatively. So if the number of charge carriers go down, then the optical power emitted will also go down, right? So you can see that for the same Im, as I increase frequency, my optical power PM will go down, right? So there is a particular bandwidth up to which the device will respond. So this is like a low pass filter function. And beyond that, it won't respond. So that gives me a modulation bandwidth, and you can see directly here the term omega m tau c, right? So it depends on the charge carrier lifetime. Again, which also physically makes sense, right? Because what is happening here is that we are trying to change the charge carrying concentration here by changing the current at some rate, right? But the maximum rate at which it can change in the active region is sort of tau c, because that's the time it takes for the carriers to recombine. Okay. Any faster changes that you do, the carriers don't really respond because they have nothing else to do, right? They can only recombine. So yeah, so the optical power emitted at frequency omega m will be proportional to Nm, right? So specifically it will be like the radiative recombination rate times, so this will be equal to N divided by tau R, which is the radiative rate, times the photon energy times the volume, because this was concentration, so that will be the optical power. Anyway, but it's proportional to Nm, right? So that means if I write a frequency response, which is the optical power emitted at frequency omega divided by at DC, and omega is 0, so this gives me a transfer function, right? Mod of h of omega, which I can write as mod of this carrier concentration, n at omega divided by n at 0. Because again, so now n, recall, this is a complex number. So what does a complex number for a carrier concentration mean? Again, it's because we are writing it as we are writing quantities as complex phasors, right? So of course, current is also not complex; it's real, right? So if you want to actually, what is the actual real current is the real part. So you add the complex conjugate to here to get a real number. But just for ease of mathematics, like for complex phasors, we just ignore the other part, conjugate part, right? So basically, that's why this is a complex number, because we're dealing in terms of complex phasors. So that just means that the carrier concentration is out of phase with the current, right? So this I can write as a magnitude times phase. So that phase is the phase difference between, so if I plot I of t and then again plot n of t, there's some phase difference here, which is the phase of this. Okay, so this is n of t. Anyway, so yeah, so we take the magnitude, because the power again is a real number that we want to compute. So we take the magnitude of this n at omega divided by n at 0. So you can see when I take the magnitude here, I take like the square root of 1 plus omega square tau square. So you can see basically now directly that the frequency response just depends on the carrier lifetime, the total carrier lifetime, because that's the only time scale in the device, right? Right, so that's the frequency response. So you can see it looks like a low pass filter. So if I plot this frequency response for the LED as a function of omega, it's some low pass filter like thing, right? So it goes down to half. So if I put this equal to half, you can see that it goes down to half at what is known as the optical 3 dB frequency. So omega optical 3 dB, where the output power goes down by a factor of half. So if you put this equal to half, you can see that this occurs at root 3 over tau c. right? So if you put this equal to half, basically, then this quantity inside the square root has to be 4, so this has to be 3, right? So you can see omega has to be square root of 3 by tau c. Right, so of course you can see that the modulation bandwidth is inversely proportional to the carrier lifetime. So the smaller the carrier lifetime, the faster they recombine, the faster you can modulate. Right, faster you can turn the current on and off. So faster you can modulate. Sometimes there is another quantity defined for the LED, which is where it goes down to 1 by root 2, so 0.707 here, and that's known as the electrical 3 dB frequency. So that's happening at 1 over tau c. Right, so this goes down to 1 over root 2 at when this is 1. Right, so when this is 1 over root 2, mod of h omega electrical 3 dB, mod of h omega square is half at that frequency, right? And so that's known as the electrical 3 dB frequency, because if we detect the light coming out of this device onto a photodetector and then measure the electrical power, right? So that photodetector, right? So you have your LED, gives out light, you detect on the photodetector, and then that gives me a photodetected current, right? So that will be proportional to the optical power. So this IPD omega will be proportional to the incident power, okay, assuming the photodetector bandwidth to be larger than the LED bandwidth. And then the electrical power here, if I measure with some load resistance, the electrical power measured here would be proportional to I square, right? I square R. So IPD square, so that will be proportional to P square of omega, or mod of H square. That's why it's known as the electrical. So anyway, so it's just different constants here, but it's inversely proportional to the carrier lifetime, which is the important thing. Okay, so again, if you take typical, so the typical values for this carrier lifetimes are, let's say, between 2 and 5 nanoseconds for in-gas P devices, which are in the telecom range, right? 1.3 to 1.6 micron. So for that, this 3 dB optical frequency, if you calculate, is in the 50 to 150 megahertz range. Okay, so with direct current modulation, that's sort of the rates at which you can go to, right? Maybe a couple hundred megabit per second is sort of the maximum rates at which you can go with LEDs and direct current modulation. Okay. Of course, you know, for optical fiber communications, long-haul links, we are operating at much higher data rates now, so we don't use this. But again, for some applications like indoor Li-Fi systems, this is still enough, so people are still interested in this. Yeah, so that ends our discussion on LEDs, and also we are out of time, so we'll end here. Any questions?
Sir,
Yeah.
I have a doubt in four-wave mixing, sir.
Yeah.
In that, you calculated one P4 out equal to eta FWM gamma L whole square P in 1, P into P in 3.
Uh-huh.
So in that, why there are three inputs, sir? There are two inputs, right? Two pumps are there. Means if
No. So
we take degenerate effect.
yeah, I mean, in general, if in general, if you take the non-degenerate case, then you could have three different input
No, sir.
frequency, which generates a fourth frequency, right? If you have a degenerate case, then two of those powers will be the same, right? So the most general case that you can consider is, let's say I have three frequencies already in the system, right? which is generating a fourth one, right? So then I have P1 power in this, P2 power in this, and P3 power in this. The generated power at omega 4 will go as a product of P1, P2, P3.
Sir,
Right?
this
So
omega 3 is...
if these two frequencies are the same, then this will just become P1 squared.
No, sir, this omega 3 is also input, sir. It is not emission.
So, I mean, as we've shown it, so what will happen is if omega 3 is already present, you can see that more omega 3 is being generated due to this process, right? So omega 3 will be amplified even further, right?
Sir, I couldn't get it, sir. Means,
So in general, all four could be present in the system already.
yes,
right?
sir. In
So so you could have all four present already. In that case, 3 and 4 will get amplified due to this process, right? Because I'm annihilating photons, so I'm reducing power at 1 and 2 and increasing the power at 3 and 4 by creating more photons, right? So so 3 and 4 could already be present, and their powers will increase or they'll get amplified, right?
sir,
And
due
the
to
power
omega 1 and omega 2.
But you could also have the case where omega 4 is not present at all. Only omega 1, 2, and 3 are present. In that case, omega 4 will be generated due to this process, right? So you could have, but if you had only two, so let's say if you had only omega 1 and 2, then this process cannot occur because then P3 will be 0. Okay, so you need at least one of these two output frequencies to be already present in your medium.
Means due to omega 3 also omega 4 will means affected.
Yeah, I mean, you can see all these four frequencies are affected, right? So P1 and P2 are reducing in power. P3 and P4 are getting amplified. But I'm saying that for this process to happen, at least three frequencies should be present. All four can be present, but at least three. If only two are present, then this process will not happen, right? If only 1 and 2 were there, 3 was not there, then P3 is 0, so there is no P4. Similarly, if you're at P3, then that will have P4 here, so P3 will also be not generated. So you need at least one of the two to be present.
Okay, so in that degenerate FWM, you wrote that omega 3 is signal and omega 4 is idler, sir.
Yeah.
So means
So typically,
what is the meaning?
yeah, so typically, so if you have one of these two present, right? So let's say in my system, so let's say these two are strong waves, so they're called pump. Okay, and then this is already present in my medium, so it's called signal, right? So what is happening? So as so let's say P1 and P2 are much stronger. So as a function of propagation distance, let's say P1, P2 are like that. Let's say I launch some small P3 power here, so that gets amplified, right? So I launch some small signal at the input. Due to this forward mixing process, it gets amplified. Okay. And not only that, there's a new frequency generated here, omega 4. So that is not present at the input, let's say, but that gets generated, and at the output now I have some power at this frequency omega 4, which I can call P4, right? So this is called idler because this was sort of like sitting idle, right? This was not input, but it's generated. So that's why it's called idle. I mean, somebody coined the term and it's stayed like so. Sometimes it's also called conjugate, signal and conjugate, because again, we had discussed this very briefly that, so if you look at the amplitude of this A, not the power, but the electric field amplitude. So the power would be mod square of the amplitude, right? So that goes as something like the product of the amplitude of the pumps multiplied by the conjugate of the amplitude of the signal. Okay, so A4 is proportional to the conjugate of A3, so that's why sometimes it's also called conjugate. So the idler is also called conjugate. But yeah, these are all terminologies, and of course, we are not going through a lot of the details here, for which you need to do a nonlinear optics course.
Okay, sir.
So you can write like coupled propagation equations between these fields to see how they are coupled to each other and how they change on propagation. Right. So, but we just very briefly discussed as to like what the final effect will be for a telecom system and what it depends on. So there's a question: can we amplify? Yeah. So both 3 and omega 3 and omega 4 get amplified, right? So the point here is that only one of these need to be present in the input, right? So typically the frequency which is present in the input is called signal. So that is amplified, and this other frequency actually was not present in the input at all. So in some sense, like it's just generated from vacuum, right? It's not amplified because there's no input, right? So it's generated and then, but yeah, we could swap their roles. So I could send an input at frequency omega 4. So then that would act as the signal. The other will act as input. But yeah, so basically these frequencies which are generated are amplified, and the ones which are annihilated are. And then there are more complicated things which can happen depending on the phase relationship between the fields. Anyway, in general, that's. So yeah, you can use this as an optical amplifier also, for example, right? So you just have some strong pump wave here, so that will be the so that will act as a degenerate pump, right? Omega 1 both. So you have a strong pump wave at frequency omega 1, and then you send in some weak signal that you want to amplify, right? So that will get amplified, and along with that, you will also generate this idler. Okay, so you can use this as an optical amplifier.